And it's my pleasure to introduce Kavita Ramanan, who's the second speaker of this first session. And she will be talking about stochastic processes on sparse graphs. So we're going from the graphon world to the local convergence world. Very exciting. Hydrodynamic limits and Markov approximations. Please go ahead, Kavita.
Thank you very much for the invitation. This has been a delightful workshop. I've already learned a lot. Can you hear me? Yeah. Okay. So this is a joint work with Dan Lacker, Robu Wu, Ankan Ganguly, Juniper, Cocomello, and several others, undergraduate students, and I will mention their names as we go along. Okay. So what I'm interested now is processes, not just the graphs themselves. So I'm interested in many phenomena are described by large collections of sort of randomly evolving particles whose dynamic interactions are governed by an underlying, possibly random graph. And so I'm always assuming that this underlying graph is locally finite so that the degree of every vertex is finite. And what do I mean by it's being governed by an underlying graph? It means that every node, I associate a label of the node to a particle, and whose instantaneous stochastic evolution of that particle will depend only on its own state or history and symmetrically on its neighbors or its neighbors. So we can get rid of the symmetry constraint very much like in the graphon by putting edge weights, but I'm going to keep it simple for this talk and just keep it symmetric. Okay, so the dynamics itself can take different forms. It can be a discrete time Markov process for each particle, or discrete time process, or a continuous time pure jump process, or diffusion. For simplicity, to get the main points across, I'm going to focus on the discrete time process and just tell you a few things about the continuous time. Okay, so of course, these dynamics are really hard to analyze exactly and even simulate. And so the goal is to develop principled approximations when the size of the vertex is large. And what do we mean by that? We just mean we want to establish limit theorems for the empirical measure, which I'll explain what that is, or the marginal dynamics of a particle, for example, in such a large system. So the outline is, first I'll tell you more precisely the model description, then talk about prior work in the dense regime, and then move on to the main thing that I want to focus on, which is the results for the sparse graphs. Okay, so just standard notation, I'll be using NV or sometimes NV of G for the neighborhood of a vertex, and DV will be the degree, and CLV or V bar is what I will use more, will be the vertex and its neighborhood, so it's the closure of the vertex. Okay. So you fix a graph in some state space, typically just think of it as if it can be 0, 1, or just some finite state space, but this can be more general. And XV, and sometimes the initial conditions are just some X, which are indexed by the vertices of the graph. And I will often put this graph and X on the subscript, on the superscript to indicate that this is the dynamics on that particular graph. So I'm going to say that this is locally interacting if it satisfies this process. So if it's a Markov process, we know that the probability for every vertex being in some set Y condition, this is a whole vector, this is just a state, of course, depends only on the entire process at Y prime. So that's all I have to specify. But I'm saying that that transition has a particular form, which only depends on the state at V at time t, as well as the neighboring states at time t. Okay. Okay. So there are many, many models, and I will explain that fall in this framework. And our framework is actually broader to allow it to depend on the history, but I'm keeping it simple again, just to bring across the main points. And so the dynamics is governed by this family of sort of transition probability matrices, ZY, which is just the usual one that I want starting at Z, what's the probability I go to Y, right, in that vertex, but it also depends on the neighborhood, A. Since it depends symmetrically, A could be a vector of any finite length because the neighborhood may be different from vertex to vertex. So that's why it's just in this space of finite sequences, unordered sequences, because it's going to be symmetric. Okay, so this is really just what we're going to study, very simple. These are called probabilistic cellular automata because it's sort of synchronously evolving. Like I said, this is just to illustrate the basic.
And the dynamics is independent for different V's? Are we
Yes.
conditionally
So
independent?
I'm going to actually, yes. So here I will make this, in the next. Yes, it's independent for different field. I'm going to make that even clearer in 2 slides, but
Okay.
yes, we are independent for it. So in the SIR model is, you have 3 states, which is susceptible, infected, and recovered. And it's governed by 2 parameters, beta, which represents the infection probability, rho, which represents the recovery probability. And so now I can give all of these states over here in terms of, the transition from susceptible to infected. So from susceptible, you can only go to infected. And susceptible to infected is just this particular expression, which you can see depends on the number of its neighbors which are infected. Okay, so the details of this expression are not too important, so I'm not. So this is just the probability that I do not get infected by any of my neighbors who are infected, right? So that's 1 minus beta is my times the number of infected. Okay.
So this is
This is discrete at this
so
time.
this is discrete time SIR, but it's not the Frost model. So your infection period is not necessarily just 1, but you have just some probability of recovering. So you could still live for many periods.
Yes, yes, indeed. You could do various, modifications of this. This is an example. So if the Frost model can be put as a probabilistic cellular automata, it can put it to the general framework, but this is just the discrete SIR model of this time. Okay. And of course, once you're recovered, it's an absorbing state. You just simply stay there. Okay, so that's one example. Then you can have the contact process, which is SIS. So sorry, the state space is just SI, not SIR. So it's just healthy and infected. So that once you become infected, you could become susceptible again and back and forth. And again, these parameters, when from going from infected to susceptible here, I've said that it's independent of because it's just your recovery time. It doesn't depend on your neighborhood. And here it does, again, in the same way that it did in the previous model. Okay, so this is just an example, and you could have many different or you could have opinion dynamics models. So, so opinion dynamics models, what the voter models, now you just have -1 and 1, and the probability that you go from -1 to 1 is, the fraction of your neighbors, which are 1. And similarly, symmetrically for 1 to -1. Or you could do majority dynamics, where you adopt the value of the majority. Okay, so there are many such. Ly is just the length of the sequence y. So that's normalized by that to have a fraction. Okay, so an elementary fact is that sometimes I will, and this makes it clear, Remco's question, which is when I have something like this and I'm saying that they're independent, you can always realize it by a stochastic recursion of this one. So it's really a simple recursion at every spot. So f of xv, then the neighborhood, and then some independent noises, which all lie in some space. You could take, for instance, always uniform 0, 1, but sometimes it's more convenient to take one only. You could take whatever you want. Okay. Okay, so continuous time Markov chains can be described analogously. I'm not going to go into the detailed definition, but just to let you know, then you would have a similar, if you know continuous time Markov chain, you have a rate matrix. The rate matrix again goes from Z to Y. And then again, that will depend, the rate matrix will depend on the neighborhood distribution as well. So you can define those models as well. Because I'm not going to go into the analysis of this as much. I'm happy to talk to people more about it, but I will mention some results. So that's why I'm telling you what model this is. Okay, so for instance, you can define the continuous time contact process. And there's a little bit of a difference. I should mention that the continuous time contact process will depend on the number of neighbors, which is why you don't want to just look at the empirical measure of your neighbors, but the number of people, people in your neighborhood, in which case that's not a nice function of the empirical measure. So you really want to look at it as these, sequences of vectors. That's the reason. Okay, and then the SIR process, voter model, Glauber dynamics for various things, etc. Okay. Okay, so what are the quantities of interest that I'm interested in? So given G in this, given some this dynamics, I'm interested in quantities like average quantities. For example, the global empirical measure, which is on trajectories here. or it could be on, this is delta is the Dirac delta mass, or it could be at a particular time. You want to look at what fraction of particles are infected or susceptible, things like that. Or here you might also be able to get quantities like what is the maximum number of particles that will. Okay. Yeah, so these capture nice functionals of averages, and that's often something, quantity of interest. Okay, so specific questions. So as we send, we're interested in approximations for large V. So as we send this, the vertex set to infinity, do these processes X, G, and Xn converge in a suitable sense to something hopefully more tractable? Do the global empirical measures that I mentioned, either in trajectory space or at the state space, converge? And often those are referred to as hydrodynamic limits. So do you have hydrodynamic limits in this context? And then can one autonomously characterize, if you just want to look at the marginal, if you're just interested in the behavior of one particle, can you autonomously characterize it without reference to the remaining particles? So of course, prior work in the dense regime, this is of course completely understood in the complete graph, and we saw yesterday in Peter's talk, it's even more complicated models in the mean field setting is known. So I'm just going to very quickly go through what this means in this sort of discrete time evolution. So you have this discrete time evolution, and now I'm just labeling them 1 to n. And then, so instead now, it's in order to just explain what the results are and why they are of that form, I'm just going to switch from this vector to depending on the empirical measure. Since it's symmetric on the vector, it depends on the empirical measure. If you don't, this is a subset of that. So this is some other function f bar. Okay, but let's look at things of this form just to see what results are well known in this context. Then, yeah, so under this simplifying assumption that you have this of this form, so under mild continuations on f or equivalently f bar, then when the initial sets converge, then you have that the x bar as well converges. So the x1n, any typical particle, converges to an evolution of a particle which has a Markovian evolution. But it's a not inhomogeneous Markov process where the inhomogeneity comes from depending on its own law, and such processes are called nonlinear Markov processes or measure-dependent Markov processes. Okay, so one way to this is just the same theorem, I just repeated to just explain very quickly why this works, because so I'm sure most of you already know, but I'm just sort of quickly repeating. So suppose this f bar doesn't depend on mu bar and the initial conditions are all IID. Okay, then the empirical measure is simply a sum of IID measures. So by the strong law of large numbers, it will go to its expectation, and the expectation of any typical particle of the delta mass is just the law of the particle. So that explains why the mu n should converge to something that's mu bar, which should equal to the law of x if there's any limit. Okay, in that case, right? And then of course, this will remain the same. That's clear because every particle is doing its own motion. So there's really no convergence. So it's trivial, right? In the simple case when they're non-interacting, it's just the strong law of large numbers. And the reason why you have the same framework in the case when it is even interacting is due to the weak interactions. And why is it weak? Because if it's dependent only on other particles through the empirical measure, the sense in which or the order in which it depends on another particle is sort of proportional to 1 over n. And so if you have nice continuity properties, that goes to 0 in the limit. And so you have this asymptotic independence and you have the same sort of result. Okay, so that's just to explain why we use also exchangeability and asymptotic independence to get these results in the mean field, and it's well known that you have. So this is actually a remarkable dimension reduction, right? So in order to find how one particle behaves in a very, very large system, you don't have to look at the whole large system, but instead you just simply look at this one-dimensional, of course, albeit slightly more complicated, one-dimensional. And so it's actually infinite dimensional in that sense, but only one particle dynamics. Okay, fine. So this phenomenon of asymptotic independence is also referred to as propagation of chaos. So of course, the efficacy of mean field approximations is well known. They work really well on complete graphs. Over the last maybe 5 to 10 years, people have been looking on what happens if the interaction is on dense graphs, not graphons for the moment, but let's say dense graphs, but with varying degrees. So of course, Shankar has done work on this. Many, this is an extremely incomplete list, just mentioning a few names. But there are, relatively recent results saying that even if it's dense, by what do I mean? I hear when I say dense graph, that doesn't make sense, only dense graph sequence, by which I mean that the degrees are growing to infinity as n goes to infinity. And often you can't just ask that the degrees go, you have to put some additional assumptions. But okay, under suitable assumptions, allowing the degrees to go to infinity, you can show that again in various situations, because you have the same philosophy that if I'm only depending on my empirical measure, then I'm still dependent on another particle inversely to my degree. And if that degree is going to infinity, then you still have asymptotic independence. And therefore, you will have, again, you don't quite have the full exchangeability. So you have to do a little more argument in the proof, but you get similar mean field results for the marginal law of particles. Okay, and then of course you can study the heterogeneous case, and this is again very, very incomplete. So just mentioning a few things where you now can use graphons, but I'm not going in that direction. Okay, so just want to say, do mean field approximations work well on any graph? They're ubiquitously used. If you look at the science literature, and if you just look at biology thing, they'll just say by the mean field approximation this, or mean field approximation that. And even when the graph, there's no reason why that graph is particularly dense or anything, it's been used. So I was sort of curious. So the discrete time SIR process, now this is on a cycle. And if you look at the mean field approximation, it's green. This is the probability of being healthy versus time of a particular particle. And you see, this is the mean field approximation, whereas the blue here, this line is a simulation. Okay, so it doesn't do too well. Not surprisingly, the cycle is not particularly dense. Okay, but the discrete time contact process, this is on a 2-tree. This also doesn't do well. The mean field approximation is really off. Okay, the full rate. Now, of course, people know, and they do ad hoc approximations called, to try to take into account, higher order approximations and correlations, but then there's no closure, so it's a little bit of ad hoc. Okay. So, and again here, there's a continuous time voter model on the regular tree. And again, you see here's the simulations, and this is the probability that you agree with exactly 2 of your neighbors. And then again, the mean field will be constant for reasons because it assumes things are independent. Okay. You could do also the pairwise approximation for this. That doesn't do too much better. It just tracks this a bit better, but it then ends up being bad here.
The root is 3 regular tree. Do you cut this off, or is it this on the infinite space?
Well, I mean, since it's simulations, it's cut off for a very large generation.
You started at the root somewhere, or do you start it everywhere, the disease?
So this is at the root.
Okay.
Yeah. This is the root and its neighborhood, because it's about agreement with neighbors. So it's the root neighborhood.
Okay.
Yes.
Wouldn't a 3 regular graph be a better approximation for infinite trees than a tree? Because if you do your simulations on the tree, the boundary plays a really important role, which you might not want. So I would expect the mean field approximation on the tree would be a better approximation for the 3 regular graphs than for the 3 regular tree.
Okay, so we will show that you could do this with the 3 regular graph as well, and the mean field approximation doesn't do well. But yeah, I just did it on the tree, but you can do it for the random. Okay, and we will see that asymptotically the 2 are same. So we've seen. Okay, so what are the results for sparse graphs? So as we saw, complete graphs and many dense graphs have the same thing, and our goal is to try to understand what may be happening on sparse graphs. And note that you cannot use this in sort of the same logic, because neighboring particles are strongly interacting even if you go. So when I mean sparse here, I mean that it remains the maximal degree, average degree, if it's a random graph, remains bounded in the limit. So I know sparse graphs are sometimes referred to things that grow like log n and little o of n, but here I mean really very sparse, that average degree is bounded, like in So the first step is, firstly, then what sequences Gn can we expect to obtain limit theorems? Because now you can't just take the number of vertices to infinity, because the topology of the graph will matter. But of course, I think in this, we know that, a natural framework to consider sequences which sort of respect the local topology is the local convergence topology. So I will just really quickly go through what is the notion of local convergence. So it's just a way to encode sparsity due to Benjamini and Schramm, and also many nice expositions in Aldous Field, Aldous Lyons, Bordenave, Van der Hoogstad. Okay, so, and many more places. So, but a graph G is just a rooted graph, is assumed to be rooted finite, countably, locally finite and connected. So rooted graphs, converge locally to a limit graph if for every K there's a large enough N such that it's the K neighborhood of the Gn is isomorphic to that of the limit graph G. Okay. And so of course, the cycle graph converges to the infinite line. The line graph converges to the infinite line. The line graph rooted at one end converges to the semi-infinite line, obvious things. Then the finite tree, if rooted here, not taken randomly, but if rooted here, then converges to the rooted infinite regular tree. And of course, the uniform random regular graph, which is what this is referring to, among all D-regular graphs, converges to the D-regular tree. And of course, this is the first non-trivial statement because this has cycles, the random regular graph, whereas this limit doesn't. And so what you're saying is that the cycles are getting larger with high probability. Okay. And then the Erdős-Schwenny graph, independent with, let's say, like C over N or NPN going to POQ over N, converges to the Galton-Watson tree with offspring distribution Poisson with parameter P. And then there are many other nice results back to 2014 by Berger, Borgs, Jays, and Saveri that show convergence of preferential attachment graphs to a random tree. So there are many, many local limits of random graphs that go to trees, as you know already. Of course, not all. Of course, lattices, finite lattices converge to lattices, but there are also other non-trivial examples. There's sort of random digraphs and things like that, which go through non-trees, which are also interesting. These are relatively easy, but this is just to say that therefore they're looking at what happens on random trees is important as it covers many examples. Okay, but we are interested in dynamics on graphs and not just the graphs themselves. So when you're interested in dynamics, you have to be interested in initial conditions. And if you have to have convergence of initial conditions in order to expect any sort of convergence of the dynamics. So how do you sort of encode the dynamics, encoding initial condition convergence? You think of the graphs marked with the initial conditions converging to the limit graph marked with the limit initial conditions. And so you need a notion of marked graphs, which is just simply putting a random variable at each node in the vertex. And again, it's the most natural way to say that you have convergence if for every epsilon greater than 0 and every finite neighborhood K, there exists an isomorphism such that the corresponding marks are less than epsilon in that neighborhood. Okay, so that's a natural notion of marked convergence. And all this notion of convergence can be nicely made Polish. And so we can talk about random elements in this space, and therefore we can have convergence of random marked graphs. Okay, so the questions that we would want to now ask is sort of results on convergence will be of the flavor saying that if my graph marked with the initial conditions converges to a limit graph marked with initial conditions, then do the graph marked with the trajectories converge to the limit graph marked with the trajectories. Okay, so that's the, so the first result, remember the first question was do the processes X, G, and Xn, and then the empirical measure converge. And so under mild continuity conditions on F, if Gn Xn converges locally to Gx in probability, and I have to explain this subtlety in a minute, but okay, first, let me just state the statement and then Gn Xgn, which is this graph marked with the trajectories, right, that start with those initial conditions, converges locally in probability to the dynamics on the limit graph. And further, the empirical measure converges to the law of the root particle. Any questions? Yes, please.
So how does this initial condition is associated with the nodes? Is that in a random form, or
you can have it random?
Or is,
so it can be IID, it could be some Gibbs measure. So
okay.
As long as you have, because the marks can be random, right? Because it's a random element of this marked space. So the marks can be random. So as long as they can converge locally, it's fine. Okay. So in fact, we do want random initial conditions when we look at things like equilibrium. So we do want random. Okay. So usually what's used is, so for just this convergence, we just need what's called convergence locally in distribution. But if you want the empirical measure convergence to a deterministic limit, then you need the stronger notion, convergence and probability. And I'm not going to go too much into that because I want to focus on understanding what this law looks like. But I'm happy to talk to somebody about it. But let me just make one comment here. Here's an example of something that converges in distribution, but not in probability. Okay, so if you take the Edershreni graph, and you take, it converges locally, right, to the Galton-Watson, as I stated. But now if I take an Edershreni graph, I take an uniformly at random vertex, and I take the connected component. That's a different graph. That also converges locally to the Galton-Watson because local convergence only cares about connected components. But it doesn't converge in probability, locally in probability to the Galton-Watson. Okay. So, oops. Okay, so thanks. So, and in that case, the limit of this is stochastic. Okay, and I'm happy to talk to people about it. But you need the stronger notion of convergence because what's in order to get convergence to a deterministic limit. And this is kind of has the same flavor as what you have in the mean field, right? Like it's the empirical measures converging to something deterministic, even though you have strong interactions, it's not weakly interacting. And yet, and you also have that the empirical measure is converging to the law of a typical particle. So you have the same thing sort of that you had in the mean field. But to tell you that it's more subtle here, that's why I wanted to say there are cases where you could converge locally, but the empirical measure will converge to something stochastic, and I can give you intuition on that if I have time after I explain what this law is.
Convergence locally in probability is basically saying that if you were to pick two vertices uniformly at random, yes, then their neighborhoods are completely independent.
Yes, it's equivalent to that. Yeah. Yes. And so you use that to say that there's enough mixing in the whole. Because you're looking at local convergence, you need k neighborhoods of okay. So you have similar results for continuous time jump processes. And I'm not going to focus on that, but I want to say that there is a subtlety there that, I have happily assumed that if you have an infinite graph, you can always sort of define the process on the infinite graph uniquely. But it turns out that in the continuous time jump processes, where I have this sort of jump rate, which can grow with the degree of the vertex, because remember my jump rates depends on my neighborhood. And in all, like for instance, in the contact process, you will have to have things that grow with the degree, otherwise it's not natural. But if you have a bound that is allowed to grow, then you could have a problem on a graph that is not maximally bounded. You could actually have graphs that are not, where you cannot, infinite graphs whose degree is not maximally bounded, you may not be able to define what you think of heuristically as this interacting particle system. So you have to put some. The degree is maximal. So that means it's uniformly bounded.
I see. So the degree
the maximal degree is
okay,
uniformly bounded. So, yeah. Not maximally bounded. Yeah. So, yeah, again.
So, but finite dissociable is probably weaker than bounded maximal degree.
Yes, and it is weaker because it allows Galton-Watson tree. So I will tell you what finitely dissociable is later, but for our purposes, it includes Galton-Watson trees with unbounded, like Poisson, unbounded, second moment, finite second moment. I said maybe finite moment is enough for this, but for some convergences, I need finite second moment. Okay, so now the question is really the main thing I wanted to get to was really what is the dynamics of a typical particle? I mean, that's the maybe not obvious thing. I mean, so far, you might say, okay, I could try to prove these other things, but and this was an open question in the context of diffusions in a paper by Delattre, Giacometti, and Dusson back in 2016, and there was really no conjecture whether this existed or what it should look like. So it turns out that the right question to ask is not whether there's an autonomous characterization just of the particle, but of the particle and its neighborhood. And that's sort of okay. It would not have been okay in the mean field set because that would be the whole graph. But here, because you're only locally finite, it's still a finite dimensional neighborhood. So you're saying, is there sort of a finite dimensional object that I can, finite particle object that I can analyze in order to understand marginals? Okay. And also you would anyway want to know the marginal, not just of one particle, but of its neighbors, because it's not asymptotically independent. So you would want to understand the correlations. So from both wanting to know what the neighborhood is, as well as really to be able to close it, it turns out the right thing to look at is the root and its neighborhood. And so we're going to answer this question for the case when G is a random tree, since that arises as local limits for many processes. Okay, and recall that in the mean field case, the typical dynamics is described by a nonlinear Markov chain, right? So a Markov chain whose transitions dependent on its own law. Okay, so this is the high level, and then I will try to give you intuition as to why this is true. So the high level answer is under suitable assumptions on the F, which is pretty broad, and neighborhood of a Galton-Watson tree whose second moment, offspring distribution has a finite second moment. Then this X evolves as a measure dependent. So again, nonlinear, but non-Markovian. So it's also history dependent process. And with the transition kernel of the following form, and I'm going to give you the explicit transition kernel later, but I just want to tell you the structure first. So if if X is the limit process, I have to tell you how it defines on all, things in the root neighborhood, right? This is the root and its neighborhood. So this transition will depend, of course, on where I am at, V at time t, okay, and my the place where I want to go to, y, just as before, that's nothing different. But this will also depend on the past of the trajectories up to that time, as well as the law of the past of the trajectories. So it is, you can think of it as a nonlinear Markov process on path space. Okay. And so, yeah, I just wrote this down in this sense. So this path, when I say, is really just a sequence in the discrete case. And this form can be given explicitly. So in fact, this is given as sort of the conditional expectation of this condition on the past of some trajectories. So that's the form that it has. And the conditional expectation, the dependence of this on the law is through these conditional expectations. So let me tell you how to actually do the marginal dynamics on the line. So suppose you had a process and you wanted to just simulate these marginal dynamics. Let me tell you what you would do. Okay, so firstly, we are interested in an autonomous characterization of -101. So if you look at that, I'm going to start with another particle system, okay, which is going to agree with this and who's going to have the law of the marginal. Okay, so what do you do at each time? Given the past and its law, I need to recursively define this family of conditional laws. So the conditional law is what's the probability that y-1 at time t is z, conditioned on the pasts of these being some trajectories. Okay, so this is the key thing that I need to know at any time t. What is the probability that this is t given the past of these two? Okay, so I have this conditional distribution. Given that, I generate these ghost particles because I need to know to evolve this, I need to know how to generate this, which is not in the system. But I use this conditional law, which is all totally autonomous, to generate the distribution of this particle in this following way. So I just need to I need to find how to get my y-2z given this, and these two are independent. I do something similar for y2, except this is swapped. Okay. And then you sample new IID noises, and then I just evolve as if these y-2 and y2 that I sampled were things that I knew like in the original system. Okay. But remember that to get my y-2 and y2, I only needed to know the conditional laws of this system. So this is the evolution. Any questions on the evolution?
So the square brackets mean the entire history, whereas the round brackets mean...
Yes, thank you. I thought I had said it somewhere, but perhaps I didn't.
Okay.
Yeah. Yes, in any case, thank you. So yes, this means the history up to time t, and this is the state at time t. Square is the history. Okay, so that's what it is on the line. And if you have the tree, you have a similar conditional distribution of 0 and of all the children condition given the paths of 0 and -1, that's what I need to evolve the whole system. And you can do this on the UGW tree as well, and it's more complicated. So in the interest of time, I'm going to tell you some other things about this first. Okay, so one thing that is nice that, okay, so you have an autonomous description, which is sort of interesting that one didn't know about. But, being the devil's advocate, it's also not very nice because it's not as tractable as a mean field system because it's infinite dimensional, right? I mean, depends on path history. But still, it at least gives you an exact limit, which maybe then you can analyze and approximate. So can you? That's the question. So like I said, so these are these ghost particles. This provides an autonomous characterization. Just key ingredients of the proof is a filtering result where you can show that if you replace the transitions in your -101, remember, you don't know the transitions of the two. If you replace it by certain conditional expectation transitions, conditioned on the past of the whole system, you can show that that has exactly the same law. Okay, but that's not very useful because the conditional expectation of -2t given the past is something I don't know. But instead, we use the conditional independence properties of these trajectories, which is of independent interest, that these XVT form a second order Markov random field in space. And there's a semi-global, which just means I allow A to be infinite as long as its boundary is finite, which is crucially needed actually in the proof. And then you use symmetries of the limit graph. And in order to do certain shifting operations in order to derive these local equations. And in the case of the random tree, you cannot use shift symmetries or rotation symmetries, but you have to use annealed symmetries, like so averaged over the randomness, and you use a notion called unimodularity to get an autonomous system. So I just wanted to, of course, I don't have time to go into exactly how all of these are used, but want to just make the point that for mean field system, we use asymptotic independence. We don't have that here. So our thing was like, okay, we need to exploit some conditional independent structure. And it turned out that this is a very useful conditional independent structure. We don't have exchangeability. So in the spirit of Peter Stock, you don't have exchangeability, but you have other symmetries. So try to exploit those symmetries to get something autonomous. Okay, but then to come back.
So I have a question. So
yes, please.
It seems that sort of you get your independence from the fact that I'm only so if I'm in this limit, the history of my different neighbors are essentially independent because I'm locally tree-like. So what I get from one side and the other is sort of independent.
So this result is on any graph. This does not rely on.
So that was my question. How can you deal with that if you're not on a tree-like graph?
I can tell you offline. But
okay.
I mean, so this is nothing to do with the tree. What comes to do with the tree is related. So these two things hold on any graph. Of course, the symmetries you have on other graphs. But the point is that I somehow need to I can exclude certain other influences if I'm on the tree. And just that gamma t is enough for me. So only in the derivation of the local equation using all this do I use the tree-like property. This is true for any graph, any finite graph. So we proved that. And I will explain this quickly at the end if I can. I just want to say something about Markovian approximations and then I will explain. Okay, so I said I criticized this result saying that, okay, it's nice, but it's non-Markovian. So can we do something better? And so, of course, when we were trying to implement things, we used a Markovian approximation of it, which is where you replace the law of the state and you replace the state, by the current state rather than the history. And so now, how do the Markov local equations work? Fair. So if you look at the discrete time SIR model, this blue thing is a simulation. The green is the mean field approximation, and the red is the local approximation, just right on the blue. So in the cycle, it seems to do very well. Well, not surprisingly, because on any UGW tree, with finite second moment, the Markovian approximation is exact for the SIR. This is joint work with Giorgio Cocomello. And the discrete time contact process, it is not exact, okay? But the Markovian approximation still does really well. So here again, the Markovian approximation this blue is the full ring, and the green is the Markovian approximation, what I call the local approximation. Red is the mean field. And now you can ask about equilibrium behavior. And again, the law of the Markovian approximation to the local equations can then be described by a system of d+1 ordinary differential equations, just using the format called Markov equations, even though they're nonlinear, again, because they depend on the law. So then the dynamics in the full tree, if it has an autopomorphism invariant stationary measure, that is also this 2 SGMRF, second order, then the marginal distribution is a fixed point of this ODE. So you can just analyze the fixed point of the ODEs to get the marginal distribution. So if you do that, you look here that if you run the local equations with starting with an IID 0.1, or you run it with a 0.9, or you run it with a half, and you run this, and you can pick up the phase transition, which is known on the tree, on the deregular tree. Because what happens, it says that here now I have two possible stationary distribution that I get is P is 0.9. So it captures the limits marginal stationary distributions for this in the easy model. Of course, one would like to go beyond reversible systems, and we do have some. Then it's a path-dependent stationary distribution. We still have some equivalences, but you want to come up with a nice example where you can analyze the local equation to say something for that. And just also dynamics, again, the voter model probability agreement, that also works well, even though here again, the Markovian approximation is not exact. So that begs the question of what we can prove about the Markovian approximation, which is sort of ongoing work when I work on anybody else to really show when the Markovian, I mean, if you can get error bounds on the Markovian approximation, this could be quite powerful in actually trying to simulate marginal distributions. I could stop here and then I could answer your question in more detail or take it offline as you prefer.
We certainly have time for questions.
Thank you. Would you be able to include dynamics of the network into your approximation scheme? And you could say, well, let's take first the easier case. The dynamics does what it does in the process that just then lives on this God-given network.
Yes.
But would you be able to include something like that?
So if you have dynamics of the, so in the discrete time case,
yeah,
yes, because if you have dynamics of the network, I think that it should not be a problem to include it. But if you have dependencies, which I also thought about, like where the graph changes depending on the values, then it's a little more complicated. And I haven't actually spent a lot of time, but it's a good question.
Interesting.
Yes. I mean, in some sense, that allows you to actually simulate things on RDE in the space, like planar motion. If you allow the edges to move depending on the vertices, on the states of the vertices. But yeah.
Have you thought about doing this whole thing as a metric measure space convergence?
So I'm thinking about it at the level of when you have a critical Galton addition. Not in this case.
Have locally the graph converge locally weakly, yes, and the interacting thing goes. I don't know how to set up, but if you set up like a metric measure space convergence, maybe they'd be more.
Yeah, the main thing is I wanted to convince myself that we can actually extract things from these equations before I make them even more abstract, but it's a good question. And I'm still trying to see how much information we can extract from these history dependent.
So I have two questions. I have my original question, yes, which I sort of don't know whether we have time for. I have a more sort of high-level question, which relates to Frank's question. Mm-hmm. So there are very simple models where you would have interaction with a network, like you have an Erdős-Renyi random graph, mm-hmm, and you put an SIR model on it. People, yes, do it often in continuum. Mm-hmm. And when I see that my friends in GNP are infected, I say, oh, that's dangerous. I don't want to go out for dinner with you anymore. So I will rewire or cut. And so people for GNP can analyze that. It's very interesting as a first order phase transition for SIR and things like that. So do you think something like that would be possible to analyze, or not some very general random graph, but things like that where you would do?
I would have to look at it carefully. I don't think it's completely out of the question, but unless I actually see if some of the properties work out, I don't think it might be related to your first question, because we use so all the other things will sort of hold here, like the things that I would be worried most about would be this conditional independence property that is quite crucial. I'll have to see how do you
Can you give an intuition?
Yes, I
that?
can. So very quickly, so I know that. So if you have this structure, right? XVT, XNVT, and then some psi VT. Okay, this is the evolution. So you might say if I condition on this, you might first say if I condition on 0, and then my -1, right, I can just plug in the value here. I plug in the value. I only need -1 and 0. So if I want to see whether this whole thing is independent of this, right? Condition on this first order, I'm asking. So you might think naively that is true. We first tried proving that because I can just plug in the value of this, and then I know how this evolves. I don't need any more information about this, because to evolve this, I only need to know this, and this is already in my system. So if I plug it in, then once I condition on this, I know how to evolve this, I know how to evolve this, and so they should be independent. But the thing is, they're not, because these noises, I was assuming that when conditioning these noises remain independent, but they don't, they get correlated because of the fact that the knowledge of this tells me something about this as well, and so therefore about its noise, because this interacts with this. But if I condition on both of them, then this information does not percolate because this only depends on its neighbor. And so if I condition on both of these, you have to show, this is the intuition. It's not, the proof is more complicated. And of course, so.
But your picture still looks very tree-like. That's the right and left.
Oh, no, I mean, it doesn't matter whether it's here. There's nothing here that I use. It's just about what I depend, right? Or what I depend on.
I see. So if there's a short loop next by, that doesn't matter.
It doesn't matter because this only, I mean, I did that because then otherwise I have to draw a larger graph. But it has nothing to do with the tree structure, right? It was just about, the argument didn't depend on anything to do with the tree structure. It was just about what information, how can my noises percolate? And if I isolate my double boundary, then the noises remain independent. The process, so if you had a Brownian motion, the process itself, the noise distribution changes, but they remain independent. So for instance, if they were driven by Brownian motions, the Brownian motions are no longer even martingales when you condition, but they're still independent processes. And that's, yeah.
Very last question.
I think you've given an answer to it, but I'm maybe we'll talk offline because I don't think yet that I've bought the second order conditional independence hypothesis or understood how strong it is. But maybe I could ask a general related question. I believe that in the work of, is it Grimmett at Cambridge in the random graphs work, they have a conditional independence hypothesis which rather resembles this and pursue its consequences. Would you know anything about that?
No, I don't know about that particular thing. What I can say is that in the context of interacting diffusion, so we found this buried after we had finished our proof to give in Deutschel's work in the early 90s or something, when he was looking at interacting diffusions, he had gradient diffusions, and they were just trying to see whether they were Gibbs. So he says that, it's still a Gibbs measure if you go across, if you start with something that's a Gibbs measure, it stays a Gibbs measure at some time t. So this is not true in general. Under certain conditions, like a contraction coefficient, he was able to show that. And if you really dig through his proof, you see that really there is a sort of second order. But he used very much that you had gradient diffusions and things like that. Whereas we've shown that we don't need that. So there's this general result. So I'm saying what it's more closely related to, if people have been asking, if I start my dynamics with IID or even a Gibbs measure, then when I evolve, will I remain Gibbs? And it's known that no, you can lose the Gibbs property and you can again then regain it and you can again become, so there are lots of work by Redding, Van Enter, maybe many people here as well. So both in spin systems and this. So what this says is, yes, you might lose that, but if you look as to that, because you're looking at the state. So that's actually a good point to make, that this cannot be strengthened to the state. You cannot, say instead of trajectories, it's second order on states. You can only say it on trajectories. If it was on states, it would be great because then we'd get good Markovian. But we know that really the marginal distribution is not Markovian. It is a non-Markovian object.
So the states really are history long.
Yes. Yeah. If you think of the states as histories, then it is a second order. But if you try to show whether the states themselves without histories are second order, then there are lots of counterexamples that in general, they won't be true.
Super, thanks.
All right, let's thank Kavita again for a beautiful talk. And we reconvene at 11.